what is going to happen. So I'll give some brief introduction. So most of the details we have
Hey,
been.
Mohan, can you turn on
Yes,
your video also?
video. I think the bandwidth some issue will come.
Okay, bandwidth issue. Okay, fine, no issues.
So
No,
that's
but
why I start.
no, but your voice is again low. I think there is some problem with your microphone. Can you hold it closer?
Yes, I'm keeping it very near, and settings.
Yeah, this is fine.
Yeah, this is yeah. Okay, I'll try to maintain that. Okay. Yeah. So this should be fixed now. Okay. So we have been seeing a lot of face field models and about the microstructure. I will give some
Hey, Mohan,
introduction.
Mohan, as soon as you start speaking, your volume goes exponentially down, low.
Okay. Okay.
So we can't hear you any longer.
Any longer. Okay.
Can you hold your mic?
Can you hold your mic? Yes, it's the mic setting. It is changing automatically. Yeah.
No, that is okay, but the online people also can't.
No, no one is able to hear.
Oh, okay. Okay.
Now, Mohan, your voice is audible when you're speaking right now. As
Yes,
soon as
yes.
you start speaking, it goes down. Possibly the proximity to the mic is changing.
I have a closest.
You're using the microphone or the
Yeah,
microphone
with
of the computer?
a headset and the mic separate.
No. Try to use the microphone of the computer itself.
Oh, microphone of the computer. Okay. Hello. How about now?
Better?
I think it's
Speak.
the same issue. Still, you are saying.
No,
No.
but this is bad now.
Again, it went down.
Yeah, I think I kept maximum mic in my settings, and
Okay.
I hope it should be working now. Whatever try to speak very loud so that it is audible to everyone.
No, I think Mohan, the issue is either you are placing something on your mic or your mic is getting blocked. So when you are talking to us normally, we can hear you, but as soon as you start your presentation, for example, at the end of your sentence, again the voice went down.
Okay. Just I'll change the headset time being. Yeah, how about now? The same issue still?
Yes.
Yes.
Yeah, you're audible now.
Yeah, okay, better. It's not fainting, right? With
Mohan,
time?
you're audible.
Yeah, okay. Thanks.
No.
Sorry for the disturbance.
Issue here.
And so
No, from where the voice is going.
Mohan, are you speaking?
still the issue is there. I'm not speaking like that. So I'm
Yeah.
waiting
Yeah.
for your
We
approval.
can hear,
We can hear you now. Yes.
we can hear you. Yeah.
So what I'm going to do is, yeah, I'll give a few slides of introduction, which is mostly repetitive of what we have seen today and yesterday, both phase field concept and computational aspects also. So for the sake of completeness and in the context of this module, so I will repeat certain points and highlight whatever required or whatever necessary for this module. So we are doing phase field model as we are using phase field model to microstructure simulations, so which are at length scales, which has been explained very well across different talks. So the idea is the diffuse interface approach, which we have been using here, where the field variable describes each phase, for example, solid or liquid, or precipitate one or matrix, so and so. Uh, so coming to the generic description, as we have seen previously, so it has a bulk contribution and the interfacial contribution. So actually, the interface defines the properties of the material, so which has different contributions. But this is being modeled in the microstructure evolution. So we will see what what model we were using, and what can be done, how we can implement programming wise, and later the demonstration of KKS OpenCL, how it is going to happen. So I'll skip some of the slides because of the similar contents, or rush through them. If you have any specific doubts, please stop and ask. And so this is the standard KKS model, which we have been talking about, where the free energy functional is described as follows, and the bulk energy and the interface energy is written in this form. The bulk energy has a contribution from thermodynamic driving force, or the double value functions. So those thermodynamic functions are written in this form, and the double value is function is written in this form. So overall, the functional looks like this. So from this functional, so before going that, just you can see how this profile of each function looks like. And so from the minimization of the energy, so we try to evolve the phase field and the composition in this case. So the phase field evolution equation is given as in this form, where you have a contribution of a thermodynamic driving force, and this is the contribution from the double well, which decides the energetics of the each phase, and the gradient interface energy term, and the kinetics, which describes the motion of the interface. So in the KKS model, at the interface, the composition is given as the combination interpolation of the bulk fictitious compositions, and these compositions are bound by equal chemical, uh, sorry, equal diffusion potential. Normally, diffusion potential we'll say, though we mention as chemical potential, it is called diffusion potential. Equal diffusion potential condition is being maintained at the interface. And the next is the composition evolution is solved. So this is how the evolution looks like. And as we have discussed in the previous talks, that because of the diffuse interface nature of the models, if you try to increase the interface width of this diffuse interfaces, there will be a fictitious solute comes up, so which will be handled through anti-trapping currents, which has been explained very well in the previous talk also. So this is a similar function which will be used in the KKS model. So this right now the KKS model is for multi-phases and multi-components. So these terms are generalized into the multi-phase or multi-component descriptions. So in overall, if we look at, I try to summarize what are the parameters which mainly present in our models. There can be others. And while I am doing the demonstration, I'll try to explain how to get this appropriate properties, where to get, and what kind of parameter, what range of values has to be chosen, so that you will get the optimum results within reasonable time, and you need not to spend much time on optimizing or deciding the parameters for the simulations. So basically, we have the material parameters as the interface energy, Gibbs energy, diffusivity, the anisotropy, which decides the interface property, and the model parameter is the height of the double well potential, interface weight, and the gradient energy coefficients, and the phase field mobility. So, and the numerical parameters are the grid size and time step. So what is happening is the evolution equations are discretized, and we found we calculate the solution in a numerical form. So these numerical forms we will do through discretization. So that's why you have a grid size, which is a spatial resolution, and the time step. So you have a time evolution, what delta increment you need to see the evolution in your transformation. So these parameters are related to each other. They are not independent. For example, if you take interface width, interface energy, it is connected to gradient energy coefficient and double well height. So interface width, so and so on. So phase field mobility is connected to the real interface mobility. If it is interface kinetics, so this is related to the curvatures of the Gibbs energy. So these are the relations which you can get eventually between the phase field parameter and the material parameter. So if you start writing all parameters, you will end up with one free variable that is nothing but interface thickness, based upon which you will choose the discretization values for given interface width. So that is the beauty of the phase field model, which is controlled by only your interface width. So the rest of the parameters are the material parameters. So one more thing I would like to mention here is, so when you do a dendritic solidification in the solidification pattern, so we tend to see a fourfold or sixfold kind of symmetry, which comes from the anisotropy of the interface energy, which is normally expressed in the form of these functions, which are normally normal vectors to the interface. And you want to rotate a dendrite, you can apply a rotation matrix. For example, it is in 2D. So in 3D, you have a 3D rotation matrix. So these expressions are simply given. All this time I spoke about a two-phase model where a solid or liquid matrix or precipitate are being described. So in these cases, we evolve only one phase field parameter to study the microstructure evolution. So if you have a multiple phases, so you need a multi-phase model, and so its description will look like this. So there are different descriptions for the phase field models describing the multi-phase systems. So I gave a generic representation over here. So you can see the gradient contribution from both phases, alpha and beta, I mean solid or liquid, if you consider. And if you rewrite this equation for the single phase description, it will look like this. So the issue is when you try to write the normals for this kind of formulation in terms of these functions, phi x square, phi x power 4 by del power del phi, which basically it's a normal to the interface. So this cannot uniquely represent the interface. So for that, what we use vectors of this form, where each interface is described through this vector. So this is basically which is previously already followed the grand potential models and other multi-phase models, just we adapted into this model. So having said that, so the multi-phase evolution is solved. Multi-phase evolution of phases and the components are solved in this model. And as I told, so the thermodynamics, so I don't want to repeat. So we have the alpha description energies and the parabolic functions and the tabulated data. So with that, I wanted to talk the implementation details a little bit more. So we have been speaking previously Professor Panikmore is also mentioning, these simulations are computationally expensive. So we use a parallel programming approach. So this parallel programming approach is common, which we do day-to-day life parallelly. So this is one example in Kitcher where you can see you can do things parallel where you can cutting the vegetable. So similarly, one example I like this cutters just like a GPU where you can do entire array process in one go. So this is I always like to emphasize this example in the context of GPU simulations, GPU computations. So this is as having this has been already discussed, CPU and GPU. So GPU are good for number crunching. CPUs are also good for number crunching, but they have other jobs to do as well, like OS are maintaining a file system and so on. So, but GPU, you have only number crunching, which provide huge computational powers. In the GPUs, so we are going to use OpenCL. So there is something known as CUDA, which is proprietary of NVIDIA, which will be talked in the next session. So I will stick to OpenCL. So this is very low level programming and can be uniquely adapted into multiple hardware. So having said that, this low level programming and compatible across different processors, it comes with a weightage of the availability of libraries. So most of the libraries may not be available. So it is very difficult to write customized libraries for each platform. So certain libraries may not be available. In that case, you have to write your own functions. So that is one drawback, con of this having maintaining adapting into heterogeneous or cross-platform architectures. If you have a specialized architecture and programming model, the optimization will be more, but you have to stick to that particular architecture. So it is vice versa of gain and heterogeneity. So it is up to user decision what can be adapted depending upon his interest or choice. So here we are going to use OpenCL, so which is going to run on CPUs and GPUs. And so what I would like to mention here is it can run on GPUs. So through the MPI, it can run on multiple GPUs. When you run it on CPUs, it is limited to one processor, one physical processor, or the processors which are available on your motherboard. So you cannot use multiple CPUs, like multi-node configuration is not possible for OpenCL. So this is one drawback, or people assumes that when you say it can run on CPU, but it doesn't run on multi-node configurations. The implementations are very limited. So you have to, if you have any issues, you have to debug and so on. And now this OpenCL model is straight away adapted into the next generation SYCL model. So the newer versions will be going to be SYCL, which was discussed in the previous lecture by Professor Panikmore. So here what I'm going to discuss about what OpenCL has. It has a host code, a device code. Host means your CPU, which handles your guest. Your guest is the device, which is what is your device? Device is your graphics card. If it is CPU, the host and device can be same, but still they treat as host and device, though they are the same hardware. So normally in the host code, so when you write codes for the GPUs, so unlike the CPU where you directly write printf command or array addition or multiplication, you cannot write the same code, you cannot execute the same code on GPU. So what happens? What is the difference? So as a GPU is an external attachment to your computer, like it goes into your PCI slot of your motherboard. So which has to be communicated, or it has to be given instructions in appropriate way so that it will do all those number crunching for you. So these instructions are called host code. So first device inquiry means we have to check whether any device is there or not. If device is there, what is the memory status? If then after the memory, and the context creation is something you wanted to do in that context for your program, and in that context you will execute your commands. So like you will execute your functions, so which are nothing but kernels which are written. So this execution process is called queuing. So queuing means one function after the other it will execute, but the entire function gets executed at the simultaneously on entire GPU. So that's why the queue for each kernel is being implemented. The kernels are written uh, and those are imported onto device and executed. So this is the standard way of GPU computation execution model. So what we will do here is, so we have a computation domain here. We will load entire computational domain, that means your array, onto the GPU, and you do the calculations and get it back. So this is the meaningful way of doing things. There are sophisticated ways of doing where computation and transfers can be parallel, but it needs special programming skills or special attention is required. So as we are looking at a package which is more generic, so we were right now limited to this aspect where you load your entire array onto GPU and do the calculations. So in this way, there is one drawback. So you are limited by the device memory. If you want to run a large domain, your device memory may not be sufficient. So in that case, you have to use multiple devices. So that is done through the MPI programming model. So this is the standard GPU architecture model. So works items are which do your computations, like in CPU, ALU, ALU, like GPU. This is what do your calculations, and it has its own private memory. And the group of these work items are called the compute unit, and this compute units together present in the device, and this is a global memory, local memory which are shared. So these are already present or left to the device or user already programmed onto the our MicroSim. So these things I'm giving a explanation for understanding of a newbie, so that if they want to go further on top of it, so this information will help. So the next thing is, so as we told, so we are speaking that if you use one GPU, you are limited by memory. So what you do is you use multiple GPUs. So now we need a way to communicate between these two GPUs. If you use two or more GPUs, you have to communicate between this GPU. Why? What happens? Here I'll explain. This is very fundamental, but for the sake of clarity, I'll explain. When you do computations, you have a stencil calculations. So you see here, for example, here X marked point, which needs neighboring points when you do the gradient calculation. When you calculate the derivative, you need I plus I minus j plus j minus 1. So, but when you try to do on multiple GPUs, you split this domain, one part onto GPU1, one part onto GPU2, other part onto GPU3, like this. But what happened now? You see the dependency for X, which is over here, is on the next device. So those are details are not known between these devices, even in the case of CPUs, because the memory is allocated for its own CPU. So that's what it called a distributing programming model. So it has its own memory. So this never know what is its neighbor to calculate the gradients. So there should be a way where we have to inform what is its neighbor value over here. So for that we create some ghost nodes. So these are the ghost nodes we create and just pass this neighbor information over here. So that's how you do this message passing interface. That's how you pass the data between different GPUs or CPUs. So if you look at a 3D, so this kind of decomposition you can check. If you are advanced, you can look into multi-dimensional decomposition also, whereas our GPU solver has a multi-dimensional decomposition. So what happens when we do actually multi-GPU calculation? So first you load your data on your machine, which is there on the CPU or a RAM, that is being loaded onto GPU, and you do calculations and get it back. If you are doing multiple GPUs and you need the communication, means you have to get the data from GPU to CPU 1 and CPU 1 to CPU 2 and CPU 2 to GPU 2. So this cycles has to go through when you are doing calculations. So why I said each GPU is attached with one CPU. So that's why you have to get it from GPU to corresponding CPU, and then CPU to the corresponding CPU of the next GPU, and then CPU to GPU. It goes on so. And so having said that, so what kind of architecture we can have, or what kind of hardware we are looking at? So we are looking at HPC machines where CPU clusters are available, and AMD graphics cards and NVIDIA graphics cards. So as I told, so CPU you can limit to only one node or one motherboard. And GPUs you can use NVIDIA or AMD. As OpenCL is supported by AMD, so if you run OpenCL on AMD, the speed up will be higher compared to when you run OpenCL on NVIDIA. So this has been observed, but you can see if you run CUDA on NVIDIA, it will be faster. So like that, every programming model has its own specific hardware architecture alignment. So that comes with its own pros and so on. So so with this basic demonstration, so basic details, we will go for the demonstration of our module. So I hope all of you have the latest version of the MicroSim. So even if you don't have latest version, no problem. I will download it along with you guys and show you how to do it, how to get it through command line. I'll try to get it quickly. So we have the MicroSim, and you can get this link. So if you are following same steps, you can get the current version of the MicroSim and do, and whoever doing the hands-on can follow the same instructions what I am doing. If you are have any doubts, please let me know. So what I am going to do is, so I'll open one folder.
So, Mohan, can you increase the size of the terminal?
Yeah, okay, sure.
Font.
Yeah. Okay, is it okay?
Yeah. Okay. Thank you.
Yeah. So I just made a folder workshop. So I'll git clone and the link which we copied, enter. So you will get the latest version. So even in the future also, if you want to get these current versions, you can do download this kind of files, and so almost 33% is over. So I think we'll complete it within less than a minute. So then we can start doing the demonstration and so on. So think so. There was a update, I think. So previously it was not supposed to be this size. So it's not, okay. We are half that. No issues. Yes. So within no time we have downloaded. So what I wanted to do. So there could be some issues. We'll try to debug and fix the issues as we go along. So let's see what going to happen. So I'll explain. First, I'll run one simulation from the available input file, and I will give you the details, how to choose parameters, and so on. So let's see. Where we go? KKS OpenCL. So I'll run one in GUI mode. So mostly later I will run all the codes for the terminal mode. So which makes us to familiarize with the terminal, and it is helpful when you run in the clusters. So towards the end, I'll try to show how to submit a job on a cluster. So there is one cluster is available at IASC. So I'll try to submit the job over there, and let's see how it is going to happen. So we'll do KKS opens GPU OpenCL model chosen. Okay, so see. Sorry. I'll start again. So if it has issues, we will have the previous version. We can demonstrate. So import in file, KKS OpenCL model, choose in file. Oh, sorry, for that I forget what I pressed. So I will choose this input file, 15 Kelvin. And so as usual, it is giving errors about what are missing and so on. So we'll have, I want to make sure everything is there or not. And then I'll run the simulation, and we'll go for the explanation later. Open. Next. So when I start, it doesn't matter when now I say 0. So for the sake of completeness, we'll keep, and next. So I'll write it as input 1, filling 1, generate. So I'll generate in my solver folder, and output 1 as my results. So it's doing, yeah. So there was some error. Okay, let's see what it is doing. And so I think it got stuck, to my knowledge. Let me see, there was some error about HDF5, no such file or directory. So that is not an issue. Oh, okay. So this has run. So I'm running on my laptop, so that's why it is slow. So you could see that it has run. So what I wanted to reconstruct. So we have written in a VTK form, so which was not able to generate. So let me make again. Check. So there was an error about HDFI. So that is the
Mohan, can you increase the font size once again? It's showing. It's
yeah.
not visible.
Yeah. Okay. So here I'm not sure how we'll increase this terminal recurrence.
Control plus.
Control plus is not working. Yeah. Thanks.
Yes. Okay. Now it's
So
visible.
this is HDFI problem. So let me locate a HDFI for my system. So this is how you debug when you get issue. So I have a local installation, but I'll use a system installation. This is the path for my HDFI. So what I'll do, I'll open the make file and add in the include path. So you see I have a HDFI path for OpenMPI, but I have here the MPI CH. So I gave the warning. Okay, let's add this path. And then we make. So it did. Yeah, reconstruct the generated. So sometimes the development paths might be different, or when you run in your local machine, the paths may be different. So this way you can debug and fix the paths. Anyway, as we spoke yesterday, the unified containers will be available so that these issues can be avoided. But if you are in a learning process, this will help. So the reconstruct what we gave, input one dot in, gave output one, and we gave number cluster 0. I think how many we gave, how many times we don't remember. So I'll give 1000. So it will finish. Okay, it ran up to 200. So that's why there's a segmentation fault. It's not detecting the 210. So the data results are available in the data. You can open with ParaView or MicroSim. So for one time, I'll use MicroSim, and then we'll do most of the things through ParaView. So let's play. Yeah, it is trying to grow. It's evolving. So it's a very small domain, you see, and a small number of time steps you can't see. So I'll stop, close this, and so even you can do it in the ParaView if you wanted to do. So where is your ParaView? And go to data. This is the output one, processor, and yeah, same thing. So it's a user choice, whatever you want to use with ParaView or MicroSim 2. Once you have the results, it's good. Okay, and then so as I told, so let's discuss what is happening with each parameter and so on. So looks like I closed the GUI. We'll open again. So this was not here. So I'll explain the details, and then we will run multiple input files for different combinations, and with that we will conclude the session. Okay, and so import new file and KKS OpenCL. So 13 Kelvin. Okay, so the first result says the dimension. So whether you want a 2-dimensional or 3-dimensional simulation. So you can see if you hover your mouse on the question mark, you will get the information what has to be given input, or some of the information are the read me about that variable. So 2-dimensional or 3-dimensional. So the mesh y, mesh z. So this is what we were talking. I was talking previously. So how many grid points you want in each direction for your discretization, and so 30 grid points we are giving the small system here, so no issues, because we are going to run on the local machine. And then, so this is the step delta x, delta y, delta s is what is the increment between each point. We have chosen 30 points. What will be the increment in the spatial? So these units are in SI units. So this is 10 power minus 8 meters is your grid spacing. And 14 into 10 power minus 9 is your time increment. So the delta t, so which you use in your simulations. So you run multiple times over a million time steps or a billion time steps for given this delta t to reach the realistic time steps which are available in solidification. If you consider a microstructure has evolved in few microseconds. So if you use this time step, you need at least 1,000 to 10,000 time steps to see that evolution. If you want a full growth, taking into account all the physics, you might run for a longer time steps. So this is what being discussed in the previous lectures. What do you want to really do at what length scale, at what time scale you want to do. So this is where you are limited. So this is 10 power minus 8 meters. So this is 0.01 micrometers is delta x. So to need 1 micrometer, you need 100 points. If you want to simulate a microstructure which you feel as a material property as at 1 mm, you see you have to do 10 power 6 grid points in each direction. If you do in 3D, yeah, so 10 power 6 into 10 power 6 into 10 power 6. That is huge numbers, which is beyond the computations power which we can access nowadays. So there are different schemes, but we do a small domain or a representative domain, actually a physical domain which captures the realistic physics of your problem. So that's why we choose. So it's not supposed to be 330. It can be 3,000 to see a reasonable growth. And given the resources limitation, time limitation, we are doing a diagram here. So number of phases, you can have phase names and number of components. So binary, ternary, and component name. So here aluminum, zinc. So they have given as aluminum is a solute which is evolving in zinc. Here alpha is evolving in the matrix liquid with a solidification. If you have alpha, beta, you have to take care of this convention when you do simulations. Otherwise, you will be evolving the other parameter where the material properties are not appropriate and so on so on. So which may not be the results what we expected. And so these are time steps what we are talking here. So with the delta x, how many time steps? This could be 100,000. So 1 million time steps or 2 million. So we will limit to small numbers as we have seen. N smooth is, so here is also there, the number of preconditioning steps for smoothing a sharp. So initially we start with the initial seed, which is very sharp. We need to avoid the large driving forces because of these high gradients. We use something known as smoothing, which takes care of this parameter. So safety, at what interval you want to save that your results. Restart, if you want to restart, how many workers you want to use. So anyway, we are going to use GPU model. We'll use one GPU, one device at a time. And here are the material parameters. You have the diffusivity of the alpha, which is solid. We have 0. And these are not relevant for the current case. Let's leave it. And the same properties for the liquid. And the gamma is the interfacial energy between liquid and the solid. So these values, so for example, you can get these diffusivity values from the literature or the databases available commercial databases or the open literature databases for your Ally system. And the interface energy which you will get from lower length scale simulations, or you can, yeah, so or you have approximations, you can tweak and guess. There are standard reported literature for specific Allies, you can use those information. So functional properties, as we discussed, the thermodynamic incorporation. So let's keep function 2, two thermodynamic phases, which we will use ALZ and TDB phase, and we have FCC A1 and liquid. So these phase names are given according to the names which are present in the TDB. Make sure that you follow same syntax, because the keywords are going to be mapped in the TDB and the Gibbs energies are going to be extracted. So these are the phase composition which we are going to compositions which we are going to input. So normally you can get these values from the phase diagram using thermodynamic softwares like thermocalc or pandat or picalphad or opencalphad. So this is 0 is represents the solid equilibrium, 1 represents liquid equilibrium, and our Ally composition is here 0.817, and you have the initial Ally composition at 870 Kelvin, which we will see later, and the rotation matrix which represents the orientation, the rotation matrix I mentioned between the liquid and the solid also. And then boundary conditions, so which we have seen previously. So you can select the boundary condition as Neumann or no flux boundary condition or periodic boundary condition. You can see each boundary is highlighted and so on. So these boundary conditions are decided based upon your conditions, whether you want a periodic system where you want to see external interfaces, or you want a no flux where your system is contained, evolution is contained within your domain. So why we are importing a shape is in the phase field simulations, we are going to provide initial seed, nucleation seed. If it is a one solid, one seed. If you have multiple solids, multiple seeds. So there are ways you can do auto nucleations, but by far phase field is a minimization, but nucleation is a involves in the increase in the energy. So these are quite contradictory. So but for our studies, we will stick to the physical seed position. So different shapes, sphere or cube or cylinder, so which helps you in deciding initial geometry of your profile. So this is for phase alpha, and this is a cube. So the information is written over here. So right now these are the generic information irrespective of the solver you will provide to the MicroSim. So now I am going to see KKS GPU OpenCL. So what it is going to take. So simulation type binary, yes, it's a binary Ally. So I'm going to write ASCII. So track progress, we will track the progress at each 10 steps. So I'll advise we better to track, especially in the OpenCL, for at larger time steps, because this track progress involves in the reduction of your entire residuals, which is not optimized for OpenCL. So their manual scripts are written, code is written, so it may not be efficient. Once you know that your code is doing fine, you can increase this interval and do the simulations. Unlike the CPU based, where you have, or CUDA based, you have libraries to do the reduction calculations. So we are not doing any elasticity or grain growth, so they are given as 0, and epsilon is nothing but here the interface width in our simulations. So that's what. So we have spoken previously that the one free parameter from the model side is the interface width, which is epsilon given over here. So you see if you remember, our grid size is, so for the sake of clarity, I'll go to the initial. So you can see the 10 power minus 7 here, 10 power minus 8. So you are trying to keep 10 grid points in the your interface width. So you have to choose these numbers based upon what kind of characteristic length scale of your microstructure you are going to resolve. Okay. In this case of solidification, the dendrite morphology, it is mainly characterized by dendrite tip radius and the velocity. So you want to resolve the tip radius as much as possible to capture the physics. So, but if you start resolving with more number of points, we lose the generality of the diffuse interface width, and also you will try to access more computational power. So you have to make a balance based upon the model and your microstructure. Choose number of points or interface width which still captures your characteristic length scale and give those information appropriately. So that is only the parameter which you give. So the rest are the material parameters what we have given or the numerical parameter. This is the model parameter. So DAB is the strength of anisotropy. We are going to give anisotropy. Here we are going to simulate four-fold anisotropy and it's a strength. So this is also calculated from the lower length scale simulations as like interface energy. So most of the calculations which involve in calculation of anisotropy also will give you interfacial energy and other properties, physical properties. So this is anti-trapping current, so which we discussed. So we will try to enable all the simulations to avoid any spurious effects because of this interface with issues, the model limitations. So right now I'm not going to use any noise and it is start. So there is no noise, so we can, it won't going to be affected, or you can keep a very high number. So it doesn't matter much now because our noise is 0. If you make noise 1, your how much amplitude you want to give. So normally we will limit 1% of noise we will provide so that your simulations are not affected by this noise. What is this noise actually? What are we talking about this? This noise is actually a random numbers generated inside the code. What these random numbers will do? So there are physical characteristics of the microstructure or the phase transformations or the interaction length scales which you cannot capture at this length scale. So those fluctuations you want to impose which decides your morphology. So as you are not going to capture it through mathematics, you are going to a random number which describes the fluctuations in your system. So which is a good representative of your physical system. There are certain rules how to provide this noise. So you have to provide a Gaussian noise and so on. So keeping within those limits. So and also you should not provide maximum noise which disturbs your physical phenomena. So that's why we limit to very few percentage. So basically in the solidification, they are like composition fluctuations or thermal fluctuations at the interface. So at the end of the day, it boils down to that, and those fluctuations we will providing with this noise in the form of random numbers. And then equilibrium temperature is the basically it is the equilibrium at which your solid and liquid exist, which we consider as liquidus temperature 870. If you see at 870 in the thermodynamic diagram, you can see the compositions which we have given in the input. And the filling temperature is the temperature at which you want to do simulations. Both are the domain temperature. So you are undercooling your system to 13 Kelvin and see how it evolves. So this is what we are doing here. And shift thermal, we are doing isothermal, and these are related to temperature gradient simulations. And then compute platform IDs and CL platform ID and CL device ID. As I told, OpenCL is a cross-platform, and so heterogeneous system. So if you have a CPU, it will exist as one platform. If you have a NVIDIA GPU, it will exist as one platform. If you have a AMD GPU, it exists as other platform. So these platforms decides which platform you have to choose to run. If you have multiple platforms, this key bit will provide. And each platform, how many devices are there? Whether you have a 2 GPUs or 4 GPUs, so that information is provided here. So here what we are providing is a platform ID. So if it is a one platform, its ID is 0. If it is a one GPU, its ID is 0. So don't confuse with this. It is ID attached to the device, just like how we index array from 0 in C program. So we'll go to next. Input 2, link 2, output 2. So it is generate. I'm generating here. Okay, and run. So you see, it is. See, I'll show you. So this is what happened. So it read. So one thing I would like to mention. So this OpenCL, as it is available for heterogeneous platforms, so it's a runtime compilation which during the program running chooses the platform and devices. So correspondingly certain variables which you have to define at that level. So that is one. Number of phases, number of compositions are rewritten from the input file to the code before the execution. So these steps has to be followed when you are changing from one system to other system. And you see that Python, there is a Python script which is read this ALZN TDB, and it found that these are the components and these are the phases, and it started extracting Gibson Edge for all the phases and the Gibson Edge derivatives, and these are written into a C program compatible header file. So without any user interference, so they are already written, and program compiled and started executing. So it shows that it shows this. So it shows, see there are one platform chosen this, and there is one device. This device is chosen. So it will print the information it executed. So this is how it runs the OpenCL code. So one thing I would like to mention here is I will follow the same instructions in the command line. So what all need to be done or what are need to be taken care when you do the simulations by yourself or porting onto HPC system. So this will help how to go about it. So what we will rerun the same simulation. What is the first step? So we'll clear the solver, and first step is Python PE data writer input. What is the file name we'll use? Input 2. Yes. So you execute the Python script which reads the Gibson edges based upon the input file. Or for OpenCL case, you have to execute whenever you change. It also decides, gives the for the runtime compilation information about the your system. That means the simulation domain information, like what is number of phases, number of components, and so on. So you see, if I execute this command, you see the same numbers popped up which you executed through the terminal. So this is what happening in the backend. So now we will make, and so make created MicroSim KKS OpenCL executable and reconstructed. So I'm going to execute npm run -np number of processors 1 because I'm going to use one device attached to one CPU, and / microsim KKS OpenCL input 2.in, link 2.in, and output 2. You see the same thing is getting popped up what you run in the GUI. So this is how it executes in the backend. The GUI will help you to optimize or to do a test case and generate your input file with appropriate parameters, and then copy that input file onto a cluster and run a bigger calculations and get the data back. So what we will do, we will try to copy this solver to the local machine I was speaking. So where we can submit a job and check for larger domain. We'll submit job there, and we will do the calculations, other demonstrations here while that job is being run. Let's see what is going to happen. So I have to copy some data. So I wanted to make sure I have very small file. So I'll copy. Meanwhile, if someone has questions, you can raise. So
You can participant can post their question on the chat actually.
So I am connecting to a server. I connected to a server which is available in IAC just behind the auditorium. So let's see. So this is a cluster we will run. So were using this input file previously. So CP, I'll make name so that we can identify what we have run. So it's better to track all the input. That I'll keep CP filling. So cluster starting. So let's see what is there. I will try to give a bigger domain and we'll submit. So we will give.
Mohan, can you increase the size of text?
Yeah. Okay. Sorry about that. Yeah. So we will give 1000 by 1000. 1000 by 1000. We will give 2 lakh time steps. Let's see how much time it will run within our demonstration time. I'll save it at 1000. So we have seen that the calculations done of function f3 are little faster compared to f2 without losing any physics. So I'll change to f3. So you will get a reasonable 1000 we gave. So have to check filling. We give 1000. So we are giving it 00. That is good. So here the clusters normally runs through jobs script. So here I have a script. So if you have a cluster, if your institute has a HPC environment, you will get these scripts over there. So I know what I'm going to do. So I'll just copy this file. So this set this is I'm going to comment npi run -np 1 /microsim _KKS _KKCL put file name output file name link cluster and output underscore cluster. Yes. So that's all. So this may not be having the info about the OpenCL and so on. So we have to copy the Python. I can't run here. So that mistake I did. Let me check whether I can execute the GE writer and my input. So that was a mistake. I should have generated this file and copy, which I didn't do. So if it executes, so these modules normally are not available in these places. So quickly, so you remember I was doing it in workshop, MicroSim, KKS OpenCL. I'll upload it there. Yes, copy and paste. It is going to get finished very quick. So you're lucky. The data transfer is faster. So this is I'm connecting to a local machine and then to the cluster. So the transferred files are here KKS OpenCL scp-r KKS OpenCL to Mohan is a cluster address. Yes, those files are copied. So now I know that these files are generated according to the aluminum zinc system and so on. So no need to worry. So what I'll do is batch script. Yeah, SQ. So 1928 is running. Oh, okay, it didn't run. Cat 1926 output. Okay, let's try to debug this. Oh, sorry. Yeah, this was overwritten when I copied the file. So if you add the time, it will show. Understood what happened. So ls, what is the input file? Cluster. So this is a new input file which is not modified. Should I change the name of the script file? Okay. Run -np1 /microsim underscore KKS underscore OpenCL input file output everything was output filling dispatch yeah so dispatch so there is spelling mistake typo sorry for that run yeah so when you run jobs on actual cluster make sure that these kinds of mistakes are not yeah program built yeah it is running just I want to make sure this is a log file written into this 31.log yeah it is running you can see so the less 1931.log it's running things are going good so let's leave that here and we'll come back later and we'll meanwhile I'll demonstrate the other things so we were doing so as we are doing here I'll open it comfortably in the file manager so this is where we are dealing our files so this is like your local space where your solver and input files are together any of your working folder and so we can maintain so we'll take this input dot in and we'll make it 3D and okay for 30 by 30 itself it was taking I'll make small very small so that we are doing the simulation and 3D is a function f3 so it will be a little faster sorry yeah this one we open link to yeah okay let it be there so we made a 3D but we need the boundary conditions also in 3 directions 1 1 1 1 1 1 1 1 so we have yeah any other changes corresponding to 3D yeah as of now I don't see anything let's see if it may throw error if it is something going wrong then we have to come back and pick change so I'm going to open terminal here so you see filling to input to I changed it so we are not changing any system I'm not going to run on Python so because we are running same ALZN without changing number of phases without changing number of components so make will do make is there already so make clean make the standard practice parent minus mp1 dot slash microsim input 2 dot in filling 2 dot in output 2. Previously we have so it is checking. So after this we will run the next simulation, and then we will go back to our cluster results whether any improvement is there, and then with that we'll end the session. And meanwhile, if possible, I wanted to show you, if time permits, so let that run. So next, meanwhile this runs, we'll open other input file, which is NILMO 3 components, so which we will save as for the day as input 4, because I know what I'm doing, and 2D. So you see this, we are going to ternary and function F4. That means we will be reading thermodynamic data from the CSV files, and we'll open the filling also. Will save as mm, 4, and we'll keep the center seed, which is curious here. We can see nice features in the simulations. Second bit point. So this input file is ready. Let's see what is happening my local. So it ran, the 3D one ran. So we know that plus reconstruct input to 2 in output 2 and one processor from 0 to 200. It's generated. Let's open with ParaView. So it compiled into one ATK file. So this was output 2. Apply. You see 3D domain has layers already. We will select alpha and the surface. You see there is our seed. We make a contour which can be seen nicely in the 3D. Sorry. So this alpha will keep outline form. They'll make a contour. Yeah, it smoothened a little bit and trying to grow. Yeah, if you provide time and resources, it will go. So what I wanted to check is, you see the surface, you can see started diffusing and growing. Eventually it will grow on longer systems, larger diamond systems. I close this, and so now we are ready with this input filling file for NILMO. So what I'm going to do, I'm going to do this Python GE and input 4.in, and so there is an error because obviously we are not reading the corresponding TDB, so no worries about that. So what I would like to mention is, when we are doing here, see here we enable elasticity also, that is good. And as I told, we need CSV files, so they are stored in TDB's encrypted folder. So you can see FCC A1 underscore 12 and the compositions L1 to FCC underscore 2. So these 3 files have the information corresponding to our simulation. So that is automatically read read by the solver based upon the phase names what you are going to give. So the suffix is same for the CSV files. So this is one thing. So without any delay, so let's run now. So that npm run fnmp1 dot plus microsim input 4.in building 4.in and output 4. So yes, it's also doing. So yeah, we'll go back to our cluster and check what is the status 931 dot log. Sorry. Yeah, it ran up to 2000 time steps only. Okay, let's copy those two files to our local machine here, and I was not sure whether Paraview is here or, but I'll try. We'll try to copy that here. KKS OpenCL to here, and we are bringing from cluster to here. Ideally, rsync will do better job. So I'll do it through rsync. So when you have multiple files updated, it will help you rsync. Progress -e ssh from there to local here. And so it is the bigger file, so it transforms slowly here, transports slowly. So okay, we'll go KKS OpenCL, and we have to do reconstruct. We used input cluster and output cluster, one processor from 0 to, I'm not sure how many RAMs. I'll give 10,000. So it will generate to whatever the files. You see the regeneration is also slow here. So okay, there is a 3000 already generated. Meanwhile, I'm not sure whether Paraview is here or not. Yeah, Paraview is here. Good. And then data, cluster data. Okay. See here, you can see this is a large domain. Unlike the previous where you see a big chunk of a red box, because your simulation domain is we are providing in a small seat. And then we'll go to the last step. Oh, it grew only very small. It will take some time. So hopefully it will finish soon and I can kill a job. It looks, the results looks good. So we can continue the job and I'll check later. And what happened to our local machine. So yeah, this there was some issue. I think I know what could be the reason. So Python data and input 4.in. Yes. Yeah, 3 and then 3 and 4. So meanwhile, what I wanted to do is so as just a quick introduction, what you need to look out when say as from my introduction. So I think so. There will be few issues because I am doing lot of things, and the OpenCL is more prone to other issues. So let me give it a try because I'm running multiple things. Any delay in query from the device, it encounters as a error. So most this mainly happens with basically with NVIDIA or this when the system hangs. So and then so this is thermocalc window. Just I will show you user what you need to look for these compositions when you generate the data from this file. So these examples, how to do phase diagram calculations are available in thermocalc example, but I need one. So you could see, yeah, this is the aluminum zinc phase diagram, which plotted as for the aluminum fraction. If you remember, we have given 870 as our liquid as equilibrium temperature. It is somewhere around here. You can see. I'm going in another. So which comes as 0.0821 as the composition. So some close value. I'll open the input file. You can see the values 0.817, and so we are undercooling to 13 Kelvin, that is 57, which is around here, and corresponding the composition is 0.91 something. It is coming. You can see here, and those numbers we can see here. 0.81, 0.926, and 909. All those numbers will come if you inquire exact values. So this way you can feed these numbers here with the help of any thermodynamic software. And when you generate the Hessian matrix and the compositions, what you have to do is basically for this solid liquid region, entire region, you have to calculate. Because this is a binary phase diagram, things might be easier. If it's a multi-component system, there could be issues with doing through this way. You need the APIs, the application programming interfaces. So that will help you to generate that data. So with this, I would like to conclude and see what was happening that. So I think, did I change something in my input file? Probably. Yeah, might be. Yeah, otherwise, I will try to conclude the session for the day. I could show that. Let me check. Yeah, okay. With this, I would like to close. Okay. There is some with might be issue with the SN data or the reading input file. So probably we will fix that later. And any questions, clarifications, and
Mohan, there is a question.
Go ahead. Yes.
Okay.
Yes.
No, you put the question. He will delay, or you can say it.
Yeah, you can come. Yes. Yeah, you can come. Sir, okay. You can come.
Excuse me, sir.
Yes, yes, please.
So the question is related to phase diagram. So can we develop a phase diagram for our own composition? I mean, we would like to cross verify. I mean, not cross verify. We would like to guess what happens to the phases.
See,
Suppose,
yeah, go on.
is it clear, sir?
See, our own composition means, what do you mean? Can you elaborate?
Suppose,
Because
yes, sir. I will put my question in another way. Suppose I am
Yeah.
having a titanium alloy. I would like to change one material, I mean one element of the composition. I would like to expect what is a drastical change in the phase diagram.
Okay. So for the most of these phase diagrams already available in the literature or through the commercial databases. So until unless you, I mean, basically the nomenclature as such is in the literature is like that. If any phase is not assessed or described through proper thermodynamics, we can do it. If it is already existing, there is no need to do. We can get the data which is available and use the data. So that is the idea. So you can change, for example, aluminum zinc to some other thermodynamic database, titanium aluminum, which is available, and put it here and run the simulation. That is possible.
Okay, sir. Thank you, sir.
So you can essentially, in the alloy system that you are considering, the databases are available. So in principle, once the database is available, the phase diagram is available. Now, if you want to just change the composition, all you need to do in terms of the program, for that alloy composition, you need to regenerate the SCN and the composition files, which can be done just as a line calculation on thermocal for that. And those line calculations will essentially feed into become these input parameter files. And then you can do any temperature, any processing that you want to do with that. So the input that is required with respect to change in chemistry is just the alloy composition. I need to have the database for that system. And the results will be as good as the accuracy of the databases.
Mohan, there is also a question in chat actually. If you can see.
Yeah, okay. I'll open it. Volume fraction of the martensite and austenite in the different zones of the element. So this is this question will be addressed in a different way. So as technically, yeah, this is possible. Whether it is possible direct way or not, it is depends upon what kind of model or what kind of system you are choosing. So basically, if you're looking at just a martensite as a phase, and which you can correlate instead of the proper phase field modeling based upon instead of the proper phase modeling instead of based on the composition and so on. So there are multiple ways to get that. It is possible actually. Martensite or austenite, yes. Because different different zone means if you have a heat affected zone or the thermomechanical states comes into the play, so you have to incorporate such stress evolutions which are inhomogeneous in nature, so that has to be taken care. Sir, Professor Rabik, you are saying something, I think.
Yeah, essentially the martensite evolution in steels, for example, includes some thermomechanical, as you were telling, I mean, it includes plasticity at the heart of it, because it's essentially a plasticity-driven transformation. Might not be able to.
So essentially, the Martensite transformation in steels is related to the plasticity that occurs during the deformation. So at the heart of doing, if you want to address that problem actually physically, you will need to include plasticity, and not just small plasticity, large strain deformation plasticity into the model, and therefore do it physically correctly. Now that is pretty challenging, particularly with respect to model formulation, and the state of the art does not exist today for including that into phase field models just yet. But there is a alternate route to Martensite transformation per se, where there are already existing good empirical models based on from Badeshia and everybody, where they relate the cooling rate and the there are nice estimations of martensitic start and end temperatures and the volume fraction that you will get at each temperature. So given, and most of these models are athermal in nature, which means if you cool it down to so between MS and MF, if you were to essentially cool down to a particular temperature, you know the volume fraction that will come out. So the temperature and therefore the volume fraction are well related, and experimentally there are already laws existing. So once you know essentially the cooling rate that you can access in your process model, and you basically can also get it in from the microstructure models that we are developing, you then can estimate the volume fraction of the martensite, which is already a relevant information which can be derived from different parts of the measurement. Okay, so that's the way we would like to include that part of the prediction into our models as our release goes on. With respect to austenite, it's pretty easier because austenite comes out of a more simpler phase transformation, and that can already be predicted from other models that we have and the solvers what we have. So does that answer your question, Prashant? I hope. Yes, sir. Okay. Mohan, there is another question for you.
Yes, yeah. Can you incorporate? Yeah, yes. We can do ternary and multi-component analysis. It's all depends upon whether you have a thermodynamic data for that. So it is possible.
So Abhik, we all this is the second Abhik, it's not me. So this is so we already had demonstrations of that yesterday, and Mohan also told you today in the NILMO system. But in principle, so you have a ternary systems with both certification and precipitation that were demonstrated. But in addition, you can also do any number of components and phases. So that's one of the strong points and the USP of the model, of the framework. And I think even Saurav will show in the afternoon a precipitated ternary precipitation. So any further questions in the physical audience? So
OpenCL needs us to declare a queue, right? A queue for entering all the kernels there.
It needs the device ID.
Yes. So if we run across, let's say, 100 devices, this code uses MPI to communicate the device thing, not OpenCL's like device ID and then running it across multiple.
Okay, I think Mohan, did you get the question?
Yeah, it was fancy. Can you repeat? Because I was part of the question. Yeah.
Let Mohan reply.
Hello, Mohan.
Yes.
So OpenCL needs us to declare queues, right? Like we have to get devices on which we will declare a queue and enqueue each of the kernels, right?
Yes.
Yes. So if we, when you are running this across, let's say 100 devices on a supercomputer, like you are using MPI on top of OpenCL, so that MPI communicates through multiple devices, or like you are using OpenCL's inbuilt device identification to, let's say, generate 100 queues, and then each queue is getting enqueued with a different domain.
No, yeah, it is the first way. So, what we do is, we have a queue. So, 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 we have a queue It is the
Okay,
first
okay,
way
okay.
what you explained. So the MPIs communicates between different uh, cards. I mean GPUs, OpenCL platforms.
Okay,
devices.
okay, okay.
So the
So the kernel execution that is internal, which goes according to the code. So the 100
So entire
GPUs when
OpenCL code goes is to one rank of MPI,
no
and then
so
each no.
no how many devices you are going to use, those many MPI processors you need. TPUs.
But the entire OpenCL code that we have will go to each of those ranks, right?
each part,
Yes,
each
yes. Yes,
Each rank of
yes,
MPI, and then MPI will have to communicate like
yes,
explicitly.
yes,
Okay, okay, okay.
yes.
Okay, that is a kind of.
So the entire code is executed on all the devices, and the MPI is used to communicate between devices. So the kernel queues is happening in each device according to our code, whatever we are executing.
Any further questions in the chat or in the physical audience? Doesn't look like. Okay, so if that's not the case, then we will break for lunch. But before we break for lunch, Mohan, let's be there. Is Shashwata there online already? Huh? Yeah. So can you just call him, and so we'll do the release of our third release now, virtually with some people and whoever is there physically, just before we break for lunch, and once we have released, then we can all go for lunch, and we'll be back by, what is the schedule? 2:15 we'll start. We'll take a 1 hour break. We'll start at 2:15. So before we do that, please, all of you who are there, please be there. You will be part of the virtual release of our third virtual release of our software. The developers, please share your videos so that you are visible. We'll try to display it online here. Try to take a picture. So Mohan, come online. Come visually.
Yeah. My camera is
Sort of. Mohan, you can unshare your screen also. Sort of. We'll need a little bit of help on the release. We'll just release it now. Huh? Yeah, he'll be there online here. So I just need help for him. What is he doing? It's coming online, right?